Okay, Claude, I think we can start.
Okay,
The room is yours.
Okay, all right. Let's speak about car performance. There is in the Formula student, and not only Formula student, in the racing community, an obsession, I have no other words, a paranoia about lap time simulation software. Don't get me wrong. Lap time is the only number which never lie. People maybe are cheating, but lap time, that's a stopwatch, that's accurate. It's accurate by 1/1000th of a second. In IndyCar, it's accurate by 1/10,000th of a second. So lap time is important. In Formula student, what do you need? You need lap time consistency, and minimum energy consumption, because there is 100 pounds for the points for the efficiency. But the problem is that I have to tell you, the majority of people are using lap time simulation software as a black box. In other words, you have a box, you put input. Oh, I changed my spring, I changed my tire pressure, shake it. Oh, look, the car is quicker. But they don't understand why. And there are different criteria, in my opinion, which are grip, balance, control, and stability. We're going to speak about it, which are extremely important to understand before you even go to lap time simulation. So this is going to be a little bit core vehicle dynamics. The first one, we're going to speak about yaw velocity. Very often I ask this very simple question to Formula student kids: what is your yaw velocity on the skid pad? And they look at me and they're not sure that they understand the question. Said, okay, roll, pitch, when you're braking and accelerating, and yaw. What's the yaw velocity? And they say 0. Yaw velocity. First of all, in which unit do you measure the yaw velocity? Well, roll, pitch, and yaw are in degree or radian. Degree is something people understand. Radian are for mathematicians. You know, nobody's saying to that the steering angle is 0.2 radian. You speak in degrees, that which is okay. What the common people can understand. So anyway, yaw is in degree, so yaw speed or yaw velocity is in degree per second. And I asked them, what's the yaw velocity on the car on the skid pad? And the guys are looking at me and they say, we don't know. I said, come on, guys, what is your lap time on the skid pad? 6 seconds. 6 seconds, it's a bad car, because now you should be in the 5-second region. But let's say 6 seconds, okay? How many degrees is there in one circle? 360. 360 in 6 seconds, that's 60 degrees per second. Ta-da! That's very simple, okay? So yaw velocity is the degree per second that your yaw is changing. Your car here is there, and when you're gonna make one circle, well, the position of the car will have changed 360 degrees, okay? All right. Now, a little bit of vehicle dynamics here. Not vehicle dynamics, physics. You know that the tangential speed is equal to the rotational speed that in all the vehicle dynamic book is written as little r multiplied by the radius. Tangential speed is angular speed multiplied by the radius. You also know that the lateral acceleration is v squared divided by r. So is big V equal little r multiplied by big R? Well, big R is equal to big V divided by little r. You also know that A equal V squared divided by R. I'm going to replace R by its value. And you are going to have that R is going to be R divided by V. In other words, you have little r equal A divided by R. And let's always check the equation here. Meter per second square divided by meter per second equal radian per second. So meter per second square divided by meter per second equal radian per second. Multiply that by 180 divided by pi, in other words, 57.3, and you are going to have R in degree per second. All right. Now, do you agree, be careful here, that on the skid pad, the speed is constant and the lateral acceleration is constant? Do you agree that on a skid pad, the lateral acceleration and speed is constant, therefore the yaw velocity is constant, correct? Good. If you derivate something which is constant, the derivate is zero. In other words, if you, sorry, I had to sneeze. If you derivate the yaw velocity, you agree that your yaw acceleration will be zero in steady state on a skid pad. Okay. All right. So you know Newton's second law that force equal mass multiplied by acceleration. In rotational, you know that the torque is the inertia multiplied by the rotational acceleration. The yaw moment is the inertia multiplied by the yaw acceleration. Let's check the unit. Newton equal kilo multiplied by meter per second square. Torque, Newton meter, equal kilometer square, that's the inertia, multiplied by radian per second square. So yaw moment, Newton meter, is yaw inertia multiplied by yaw acceleration, okay? And basically, in mathematics, you're gonna have 12 codes for the yaw moment. Fy, 4Fy, 4Fx, and 4Mz. So, for example here, the two forces on the front here multiplied by A have a tendency to rotate the car to enter in the left-hand corner, for example. If I go to left-hand corner, these two forces on the front will rotate the car this way. But you are going to have an anti-yaw moment of the two rear tire. You still need to understand that you cannot calculate the yaw moment unless you have the Fy and the Fx and the Mz, ta-da, unless you have the tire model, okay? So anyway, on the two rear, multiply the two rear Fy multiplied by B will create an anti-yaw moment, okay? You have here also that, for example, if I only brake on the left, the two orange line multiplied by the half track, and be careful that the track on the front and the track on the rear are not necessarily the same. If the two force in braking on the left will help the car to rotate to the anti-clockwise, but the two force on the right will help the car to rotate clockwise, okay? And then you have the 4MZ. Most of the time, the lateral grip is 70 to 80% of the reason why you have a yaw moment. So the blue force are usually the biggest one, and the orange one, small one, and very small one, the MZ, okay? All right, now, let's take an example here. You have the speed versus the time, and let's say that this is car A, okay? And I'm saying I'm a Formula One engineer, and I say to the guys, you need to work on the car because we are losing grip, we are losing time compared to a competitor at the apex. The top speed is good, the engine is good, the fast corners are good, the braking is good, the acceleration is good. It's in the slow corner that we are missing, okay? All right. So I want you to find me 1 or 2 kilometers an hour at the apex, okay? So you understand that, okay? Now, the thing is that the lateral acceleration will have to be more and earlier. Earlier, you're going to have a delta time. So let's say you are gaining 1/10 of a second. Whoa, 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 whoa. 1/10 of a second is a lot. In Formula One, if there is 10 corners and you gain 1/10 of a second per corner, you are gaining 1 second. So we are dreaming. But if you want to have more grip, okay, you want to have more grip, more speed earlier. If you are on the same radius, more speed on the same radius means more lateral acceleration. So you need more lateral acceleration, but you need more acceleration sooner. And let's say that if you gain 1/10 of a second, that means that the peak of lateral G is 500 of a second earlier. Good. Now, your car will have rotate, let's say it's an hairpin, 180 degrees, and you agree that you will have finished the 180 degree earlier, okay? If you integrate the yaw velocity, if you integrate degree per second, you're gonna have degree. So if you have an hairpin, you make 180 degree, fine. Okay, now, let's start to look at yaw velocity. You agree with me that, okay, if you do your skid pad, okay, let's go here. I'm gonna go there. If you do your skid pad here in 10 seconds, you have a yaw velocity of 36 degrees per second, okay? If you do your skid pad in 5 seconds, where your yaw velocity is 72 degrees per second, okay? Same degree, less time, more yaw velocity. So you agree with me that you are going to have more yaw velocity when you are going faster, okay? More yaw velocity, okay? And not only you're gonna have more yaw velocity, but you're gonna have it earlier, okay? Now, ta-da! Let's look at the slope of the red line and look at what we call the yaw acceleration, okay? So yaw acceleration is the derivative of the yaw velocity. And you agree with me that if you go on an hairpin, you're gonna need more yaw velocity variation. So you're gonna have more degree per second square earlier. It's nothing else than the derivative, the slope of this baby here. You agree? So here, you agree that the yaw velocity is constant. When the yaw velocity is constant, that's when the yaw acceleration is 0. So you want to have more yaw velocity earlier, therefore more yaw acceleration, okay? You will understand that the yaw velocity, the yaw acceleration is 0 at the apex, which means what? Be careful here. You remember this, allow me to go backward. You remember that the yaw moment is the inertia multiplied by the yaw acceleration. That means that if the yaw acceleration is 0, the yaw moment is 0. So you have an example here where the yaw acceleration is 0. That means the yaw moment is 0. So now we are going to look at the yaw moment. Here you have the yaw acceleration. Look very carefully to the y-axis here. You have now the yaw moment, and the yaw moment is nothing else than the inertia multiplied by the rotational acceleration, okay? So basically, if you allow me, there is no difference between these two graphs, yaw acceleration, yaw moment. The difference is that we change the unit of the y-axis by multiplying the yaw acceleration with the yaw inertia, kilometer square, okay? So you are going to have basically a yaw moment, which is going to go higher at the entry. More yaw moment allow the car to rotate faster at the internal corner. More negative yaw moment to extract the car from the hairpin. And you cannot go from positive to negative without passing to zero. So at a certain time, your yaw moment at the apex will be zero. So basically, your lateral force will go like this, but then you need more yaw moment. And may I remind you, where did you get the yaw moment? 90 or 80% is from the blue force, the lateral grip. So that means that if you want more yaw moment, you need more blue force on the front or less blue force on the rear. So I'm going to go here. Oh, sorry. You are going to have, you add here the lateral force like this on the front and on the rear. No, and that was the total. Now you need more lateral force on the front and more lateral force on the rear. But if you look very carefully at the entrance of the corner, you see that you have a gain of front bigger than the gain of rear. And you see that the exit, you have a gain of rear bigger than the gain of front. Okay, you want to go faster. If you want to go faster, you need more grip. That's clear. You need more lateral force. How do you get that? More downforce, better tire temperature, better camber, better slip angle, better Ackermann, better weight transfer, and so on. So you need more grip. But you also, if you want to go faster, you also need more yaw moment. Okay. In other words, you need to rotate the car much quicker. And how are you going to create the yaw moment? By looking at the difference between the front and the rear grip. So let me show you real data here. You have an example here of, in blue, the front lateral acceleration, and in red, the rear lateral acceleration. And you see that the front is more G on the front than on the rear. Then at the exit of the corner, it's the G going down much quicker on the front than on the rear. So here you are creating more grip, front and rear, guaranteed, but you have a variation. Look at that. I look at the front minus the rear here. You agree that you have here at the apex the same lateral G front and rear, but at the entry you have more grip on the front than on the rear, which help the car to rotate. And how do you calculate that? Because once again, you're going to do the yaw moment. Oh, sorry. Home. Once again, you're going to do grip on the front multiplied by A minus grip on the rear multiplied by B. That's going to give you the yaw moment coming from the FY. So you have an example here, again, where you see that the grip on the front increase quicker than the grip on the rear, but decrease quicker on the front than on the rear. So you are going to have here the variation. It's not a lot, 0.08 G, okay? And you see, by the way, that at the apex, it's going to be 0. In other words, what's happening in the apex is for a mini moment, it's a little bit of steady state, okay? And here also, when the G on the front and on G on the rear are the same, it's steady state. Now that's interesting because we look at the gyro and you see that the yaw speed is going the quickest at the apex about what? 20, 15, 17 degree there. But look at this. If you derivate the yaw speed, you have the yaw acceleration. And that you see that, oh, I didn't play with the data. It's the reality. Do you agree that at the apex, the yaw velocity is constant? If the yaw velocity is constant, the yaw acceleration is 0. If the yaw acceleration is 0, that means the yaw moment is 0. And if the yaw moment is 0, that means that, again, you have the grip on the front multiplied by A equal to the grip of the rear multiplied by B. So basically, I'm going to go back to my slide here. If you want to go faster, you need more grip. Everybody understand that. If you want to go faster, you need more grip. But also you need more yaw moment. You need to rotate the car quicker. If you want to go faster in the corner, you need to have more rotation power, more possibility to rotate the car. And so basically you want to have more lateral acceleration and more yaw moment. So let me show you how a yaw moment versus lateral acceleration graph would look like. Basically, in point number A, just before they enter the corner, you see there is no steering yet. You have no yaw moment and you have no lateral acceleration. At point C, the yaw moment will be the lateral acceleration will be maximum. But you remember at the apex, the yaw speed, the yaw velocity is constant, so therefore the yaw acceleration is 0, so therefore the yaw moment is 0. The yaw moment is 0 at the apex, okay? And so you are going to have here the yaw moment 0 at point C. Now, to enter the car, you need a positive yaw moment. You have to be careful about the convention of sign. We decide that a yaw moment positive is when you have something anti-clockwise and clockwise is negative. So you need to have a yaw moment positive to enter the corner, okay? And that's why in B, which is somewhere, because you remember the yaw moment is 0 here and the yaw moment in point A, and the yaw moment is 0 at point C. So it has to change and it's going to go from A to B to C. And as you can see here, the yaw moment go from A to B to C. And then you need a negative yaw moment because you need to extract the car. Because if you are there, then you'd go on a skid pad and the car will be on a circle and will never get out. So now you need a negative yaw moment. In negative yaw moment, it means that the grip on the rear multiplied by B, the distance B, will be bigger than the grip on the front multiplied by A. So you are going to go from C to E, going back through the point D where you have, look at that, the maximum negative yaw moment to extract the car there. Okay, so you start to understand that, okay, quick summary already after 15 slides. On a race car, you want maximum grip. How do you get its maximum grip? Give me better tire, give me better downforce, give me the right camber, the right slip angle, the right temperature, the right pressure. That's why you need to understand your tires. That's the number one thing to do. Okay. Second one, you want to have the right amount of yaw moment to rotate the car. And here is given already a little intuitive explanation. If you have too much yaw moment, you have an oversteering car. If you don't have enough yaw moment, you have an understeering car. If you have too much yaw moment, oversteer. If you don't have enough yaw moment, understeer. So let's say that you need here at point B, 2,000 Newton meter. I'm putting a number just like that, 2,000 Newton meter. If you have 2,500, you have an oversteering car. If you have 1,500, you have an understeering car. Okay. The question you have is that, yeah, I understand that. How in the hell do I know that 2,000 is the right number? I will explain that to you. This is an example of simulation where you have here the fx, the change, may I insist, the change in fx, the change in fy, the change in yaw moment and the change in lateral acceleration. Now you are speaking about 700 of a meter per second square, which is lateral, which is 7,000 of a G. That's not a lot. And the change in longitudinal acceleration. So you see, for example, that when I increase the front grip there, okay, I can have a change of yaw moment like this, but look at that. I can increase the grip on the front, and that's going to give you more yaw moment. But I can also decrease the grip on the rear, and that's going to give me more or less yaw moment. So again, look at that. The yaw moment is what? The 2 front grip multiplied by A minus the 2 rear grip multiplied by B. To increase the yaw moment, you can either increase the front or decrease the rear. Yes. That's, by the way, the reason why some rally driver, they pull the handbrake. They pull the handbrake because by decreasing the rear grip, they are going to be able to enter the corner faster. But, big difference. If you increase the front, you increase the lateral acceleration. If you decrease the rear, you decrease the lateral acceleration, okay? Now, here's an example where I increase the front a little bit and decrease a little bit. You see, by the way, that I increase the right side more than the left side because you are in the left-hand corner, so you're going to have weight transfer. And I decrease the right rear more than I decrease the left rear. But you could imagine to do that with the braking, okay? If I brake more with the left or I brake less with the right, I can change my yaw moment also and having a difference in deceleration or but no difference in the lateral grip. So basically, let's make sure you understand it. The yaw moment is the grip on the front multiplied by A minus the grip on the rear multiplied by B. But on the other hand, the lateral acceleration is F equal ma. If you make the sum of the 4 Fy divided by the mass, you have the lateral acceleration. And that is an example of a car at Sebring where we calculate the yaw moment, which vary between 1800 and 1800 and minus 1800 Newton meter, okay? So you see that the yaw moment is changing, and you see that, for example, here at the entry of the corner, you have yaw moment which are more in the green zone, and at the exit of the core more in the blue zone. So you have a positive yaw. Here, for example, you have an hairpin. You're in the blue zone to enter the corner and the red zone to exit the corner. Okay, blue zone and so on. Okay, now you have 3 causes of slip angle. Sorry, I'm helping myself a little bit with tea here. So you have 3 causes of the slip angle: the delta, beta, and R. Don't worry, I'm going to explain that to you. So when you are beta is the yaw angle of the car, okay? And then delta is the steering. And then from there, I can calculate the slip angle that I have on all the tires. And guess what? If I know the slip angle and the vertical load on the tire, and I have the tire model, I can calculate the grip on each tire. So that grip, right rear, plus that grip, left rear, plus that grip, right front, plus that grip, left rear. I do the total of these 4 grip, divide by the mass, I have my lateral acceleration. And I do the 2 front grip multiplied by A minus the 2 rear grip multiplied by B. And that is going to give me the yaw moment. So there are 3 causes for the slip angle. Delta, so you agree me that you create a slip angle on the front. By the way, the slip angle here and the slip angle there are not necessarily the same depending the Ackermann that you are using. Second one, you have beta. So you agree with me that that is the direction in which the car is going, and that is the direction in which the tire is pointing, and that is creating a slip angle on all four tires. And then, that's the biggest mistake that people do not understand. You have a yaw velocity. You remember the car is like this and will be turning. So you remember if the car is making 360 degrees in 6 seconds, or let's say in 10 seconds, 360 in 10 seconds, it's 36 degrees per second, okay? That you can measure with the gyro, by the way. So let's make a little calculation about the little r. A lot of people are missing that. Okay, you agree that if when the car goes straight, that's the Vx and it's everything the same. But you are going to have a yaw velocity. So you are going to have here an additional tangential speed on the rear, and that tangential speed is going to be little r multiplied by b. B is the distance between the CG and the center of gravity, okay? And r is the yaw velocity expressed in radian per second, okay? So radian per second multiplied by meter equal meter per second, okay? Of course, it's going to be the other way around on the front. If you turn this way, you have an additional, well, a subtractive tangential speed, little r multiplied by a. But then you are going to have also a tangential speed which is increasing on the right side and decreasing on the left side. And to do that, you need to multiply little r in radian per second, your velocity, multiply by the front track or multiply by the rear track. And here you need to subtract, the yaw velocity multiplied by the front or by the rear track, okay? And so that's gonna give you the calculation of the slip angle that you have on each tire. So you have here that the slip angle on each tire is a function of Vy and Vx, and arc tangent of Vy divided by Vx is giving you the angle beta. It's going to be a function of the yaw velocity and A and B, so the weight distribution is going to be, the wheelbase and the weight distribution are going to play a big role. And it's going to be a function also of the front track, or the half track front and rear, minus the steering angle. And may I remind you that the steering angle left front and right front is not necessarily the same on the is not necessarily the same on the left and on the right because of the Ackermann. Okay, so I want you to understand what I'm going to do here. You have now the ability to calculate for a given beta. Beta is the yaw angle, and a given delta steering. You can calculate what the slip angle is on each tire, and what, because you have the tire model and you know the vertical load, you are able to calculate the lateral grip. And if you have the lateral grip, you can have two things. You can have sum of the 4 grip divided by the mass, lateral acceleration, and sum of the grip on the front multiplied by A minus sum of the rear grip multiplied by B equal the yaw moment. So look at this. Imagine, guys, that I'm going to increase the wheelbase. Do you agree that if I increase the wheelbase, I change my force slip angle? If I change my force slip angle, I change my 4 lateral grip for the same tire model. If I change the 4 slip angle, I change the 4 lateral grip. If I change the 4 lateral grip, do you agree that I'm changed the lateral acceleration For the best or the worst, I change it. 0.1% or 5%, I don't know, but I change something, and I change the yaw moment. So I change the grip and I change the balance. The grip is the sum of the 4 grip. The balance is the yaw moment. So when I change the wheelbase, I change the A and the B, and I change the slip angle. So I change the lateral grip. So I change the total lateral acceleration and yaw moment. If I change the weight distribution, let's say I move that car forward and backward. If I change the lateral acceleration, I'm going to change the weight distribution. I'm going to change all 4 slip angle, and I'm going to change the A and the B. I will change the lateral acceleration. I will change the yaw moment. Okay. Let's change the rear track. I increase the rear track a little bit, and you agree I'm going to change the 2 rear slip angle. If I change the 2 rear slip angle, I change the 2 rear grip, I change the lateral acceleration, I change the yaw moment. If I change the front track, same thing. If I change the front track, I change the two front slip angle, I change the yaw moment and the lateral acceleration. If I change the Ackermann, I change slightly these 2 slip angle. I'm going to change the 2 grip on the front. I'm going to change the lateral acceleration, and I'm going to change the yaw moment. If I don't change anything on the car, nothing, but I switch from a Michelin to a Goodyear, for example, then the slip angle remains the same, but because it's not the same tire model, the green vector, the lateral grip, are not necessarily going to be the same. Aha. So that is going to change dramatically the lateral acceleration and the yaw moment. If I change the rear toe, let's say on the rear, I'm going to put more toe in or less toe in, I change the 2 slip angle on the rear, and I'm going to change the lateral grip and the yaw moment. And same thing like that. And I can do it with the wheelbase, the weight distribution, the toe, the Ackermann, the track, and I can change it also the anterior bar and the springs, which are going to change the vertical load. And if you change the vertical load on the tire, by changing the slip angle, you are going to change the lateral acceleration and the yaw moment because you change the lateral grip. So let's imagine that for a given speed, I'm going to make an array, let's say an Excel spreadsheet, where I'm going to put beta at 0, but with different steering angle, or I'm going to do delta at 0 with different yaw angle. Okay, so but I'm imposing the speed. Okay, so this is a theoretical calculation. I don't know which steering angle I'm going to use. I don't know which beta yaw angle I'm going to use, but I'm going to make a theoretical calculation, and I'm going to create a grip of the yaw moment versus the lateral acceleration. So may I insist, yaw moment is the balance, lateral acceleration in G. You see that's a race car, you can have nearly 3.3 G there. And I'm going to have ISO line of different beta and different delta. So beta is the yaw angle. You see, by the way, that when you are at beta 0, okay, on the line 0 there, you are going to have lateral acceleration 0 like this, okay? So these are the ISO line of the yaw moment versus the lateral acceleration with different beta. Now I'm going to do also here is different delta, and here the delta are the delta at the steering wheel, okay? And so now I'm going to combine the two together, and I'm going to have the famous yaw moment diagram, which is occupying 6 chapters of the Millikan book. So that means that there is something there, which is the crisscross of different isoline of beta and different isoline of delta. So each one of the crossroad between a given a given isoline of beta and a given isoline of delta, like here, for example, is corresponding to one of this Excel spreadsheet situation. So for example, here I have delta of 40 degrees and delta of -2 degrees. Well, I'm going to take delta minus 40 and beta 2 degrees, and I'm able to find what is the corresponding situation there. So that's interesting because for a given speed, may I insist, for a given speed, so I have a huge parking lot, I impose the speed at, I don't know, 100 kilometers an hour, and I'm going to say, if I turn the steering wheel 20, 40, 60, 80 degrees, and if I yaw the car 2, 4, 5 degrees, and so on, what will be the G that I'm going to have, and what will be my yaw moment? What does that mean? That here, it's going to give you the maximum G that that car can get at a given speed, and in that case, if you make a zoom of that, you will know what's the steering angle and the yaw angle that you have to have on that car. Now, there are 2 ways that you have to understand here. When you were a kid, you have been told that y is a function of x, okay? So give me the curve and give me the x and I will give you the y, okay? So you have 2 input here, you have the function and you have the x, give me the y. Here is different. You have to understand that on the yaw moment diagram, the y and the x are output. The yaw moment on the y-axis and the lateral acceleration on the x-axis are output, where the speed and the yaw angle and the steering angle are input. So you have 2 solutions. Either you are going to have the yaw moment n and the lateral acceleration, which are going to be a function at a given speed of the beta and the delta, or you can have on a given radius what is going to be the beta and the delta. For a given beta and delta, what are going to be the yaw moment and the lateral acceleration? Okay, so this is an example where you are at 150 kilometers an hour. This is an example where you are on a given radius of 50 meters. Okay, so let's try to understand what you do with this. Okay, so you have a yaw moment at a given speed. Okay, and you see that here you can look at the yaw moment as the balance. Okay, or and here you can have the lateral acceleration that can be expressed in G, or that can be expressed as meter per second square. But you agree with me, look at that. What does that mean? I impose the speed. If here, my radius, my yaw angle, if the car is symmetrical, if you have a yaw angle 0 and the steering 0, that means you are in a straightaway. If you are in a straightaway, the lateral acceleration is obviously 0, and the corner radius is, when you have beta 0 and delta 0, you are in a straight line, so the radius is the infinite. Now, if I get a huge parking lot, and if I lock the speed, and I have a given lateral acceleration, that means that I have the minimum radius. If I have a lot of grip, I have minimum radius, and I have maximum yaw velocity, okay? So you see that the yaw velocity is 0. And here you have more and more yaw velocity in degree per second or radian per second, and the minimum radius. So that's what it means, okay? But if you have the inertia, you also can calculate what the yaw acceleration is in radian per second or degree per second. That is a mistake. I need to correct that. I don't know if I can do it. Yes, it's degree per second. Sorry about that. So obviously the yaw velocity is 0 there. No. Yeah, it's degree per second square. It's a yaw acceleration. Then maybe maybe I was right. Yeah, maybe I was right. It's not the yaw speed, it's the yaw acceleration. So basically, it's going to help you to understand the balance of the car. If you are here, you have an oversteering car. So in other words, okay, what does that mean? Let me explain to you. Number one, the maximum G, the maximum lateral acceleration that car can have is here, 3.35 G. Good. And then if you make a zoom, it will tell you at which beta and which delta that lateral acceleration is going to be used. Houston, we have a problem. Haha. What's the problem? The problem is this. Allow me to go backward at full speed here. Where do you have the maximum lateral acceleration? The maximum lateral acceleration is the apex, correct? And you agree that at the apex, the yaw moment should be 0. The maximum G is at the apex and the yaw moment should be 0. Well, let's go back to this thing. You agree with me that you can see that here, the maximum lateral G is 335, but the yaw moment is not 0. So there are two ways to look at that. If you want the yaw moment to be 0, then the maximum G that you can have is 3.22. If you want the maximum G to be, you're going to be 335, 336, but then the yaw moment will be positive, which is telling you that you have an oversteering tendency. So that is the maximum amount of lateral acceleration that you can achieve by having the yaw moment 0. So the car is neutral. And that is the yaw moment that you can still have from the front tire if you want to go faster. Okay. So that is the yaw moment still available on the front tire there at when you are there. So when you are there, you are not using, you can have more yaw moment because you are not using the front tire at the maximum yet. Sorry, need to have a little drink. All right. Now let me show you an example. Here is a yaw moment versus lateral acceleration. So the balance versus the grip for two different setup. Honestly, I did that slide many, many years ago. I don't even remember what I changed. But you can see that if you make a zoom there, you are going to see a little difference between, I don't know, it's going to be less than 1/10 of a G. But you know, you are in racing, and you know, 1/10 of a G is a big difference. Let me show you what you can do. This is an example of the yaw moment versus lateral acceleration. So you go between minus 50 to plus 50,000 feet and between minus 3.5 G. And you do that with different speed. And guess what? Why is it that you change that? Well, you have speed, so you have downforce, and you remember that the downforce is a function of the square of the speed. And then it's going to give you a different yaw moment versus lateral acceleration. Now, you don't see that, but I'm going to do this here, and I'm going to go there. Okay. You barely see it, but this is a car I really like, and I'm going to tell you why. It's that you see that the peak of the red, and red is high speed, 250 kilometers an hour, is negative, and the peak of the green, and I want to show you green is 50 kilometers an hour, like that, okay? So you see that the peak of the green is slightly above the zero line, which means oversteering, and the peak of the red, high speed, is slightly under the zero line. This is a car, I know that car, I'm not going to tell you what it is, but that's a car which won races and championship as a consultant from this team, this company. I like that car because we made the car slightly oversteering in the low speed corner and slightly understeering in the fast speed corner, and that the driver really liked that. Now, the notion of control and stability. Okay. First, before we speak about vehicle dynamics, what is control? Control means you are in charge. You decide, the car is obeying to you. You speak to the car understands and tell and do what you want to do. You are on the snow. You turn the steering wheel and the car goes straight. You are a passenger. You are not in control. The car controls you. You don't control the car. You turn the steering wheel, okay. You turn the steering wheel and the car goes to the apex the way you want to do, you are in control, okay? So that's the physical, logical, intuitive explanation. Control is, you know, in aircraft, they speak about authority, okay? So the guy with the stick and the guy does that, is the airplane doing what you want it to do, okay? Now, there is a way to quantify that, which is the amount of yaw moment that you create per degree of steering angle. In Formula Student, I keep asking that question all the time. Can you define control and stability, and can you tell me in which unit you measure them? Okay. So control is, I turn the steering wheel, how much yaw moment, how much pivoting power do I have when I rotate the car? So I'm going to turn the steering wheel a little bit. I'm going to create a slip angle on the front. Because I create a slip angle on the front, I create grip. Grip on the front multiplied by the distance A is going to create a yaw moment. So basically, but in quasi-steady state, we are going to consider that the beta is equal to 0. So let me go back to the, let me go back to the graph here. I'm going to move on a beta 0, and I'm going to go from a delta 0 to delta 1. So basically, what I'm going to do is I'm going to, let me do that with some animation. I'm going to circulate on the beta 0, and I'm going to go from delta 0 to delta 10 here, okay, from 0 to 10, okay. And you see that because of that, I create a yaw moment of 500 Newton meter. So my control in that case is 500 divided by 10 equal 50 Newton meter. Okay. So let's change something on the car. And if I change something on the car, I'm going to have a different yaw moment. For example, I put a stiffer front actual bar here, and you see that 10%, and you see that my control went from, how much is it? From, I don't know, well, yes, from 50 to 42.3. So you start to understand the advantage here, because now you're going to be able to create parametric. So how much is the handlebar bar changing the balance, the grip, and the control. And there is another one, which is the stability. So before we go to a vehicle dynamic explanation here, what is the stability? Stability means you continue what you do to do what you are doing, stable, okay? So if you go on the straight and your car goes straight, it's stable, okay? So how do you define that? I'm going to yaw the car 1 degree, and by changing without steering, so imagine, okay, I'm going to give you a picture here. The car is in the braking zone, and there is a giant coming from the sky, put his hand on the car and yawing it 1 degree, and then remove his hand. And the question is the car coming back? So the driver doesn't turn the steering wheel, you yaw the car, because of that you change the force slip angle, because of that you change the fore lateral grip, you are going to create an anti-yaw moment, and that's why stability is with a negative number. And so I just wanted to be sure that everybody is still there. So you create an yaw angle. Because of that, you changed force slip angle. Because of that, you change fore lateral grip. Because of that, grip on the front multiplied by A and grip on the rear multiplied by B, you are going to change the yaw moment. Okay, so in this example, I'm going to lock the steering at 0, and I'm going to say I'm going from beta 0 to beta 1, and you see that you have, yes, a negative number because you want to have a yaw moment against the variation. That's what is stable. You yaw the car to the left, but you need a yaw moment to the right, okay? So, that is the stability that you have there. And here you have the lateral acceleration, the stability. If you change the front anti-roll bar, and you see that you are a loser when you change the front anti-roll bar and you change the stiffness there. So now this is the example of the control and the stability that I showed you here are the one at the entry of the corner. Okay, because you see the beta is 0 and you change the delta, or here the delta is 0 and you change the beta, but you are at the entrance of the corner. Nothing prevents you to calculate the slope on a given ISO line of delta and going from one beta to another, or the slope for a given delta and changing the beta. Stability and control can be measured not only at the entry, but at any point of the car, of the circuit. So example here, I have my beta 4 degrees, okay? And I turn the steering wheel from 60 to 61. Do you still have a yaw moment there? Here, I lock the steering at 60 and I have a yaw angle of 4 to 5 degrees. You see that on racing circuit, NASCAR, for example, you see a car like this, and you have another car with the right front touching the left rear. Is the car going to go back, or is it going to go in big pivoting, big spinning? Okay. So now, let me give you an example of a good and a bad car. This car is good for 2 reasons. You are using lateral grip versus slip angle. You use each of the tire, left front, left rear, right rear. You use each of the tire at the peak slip angle. Fantastic. You did a fantastic job as a race car engineer and a driver and so on, okay? And on top of that, if you do grip on the front in red and in green, multiply by A, and grip on the rear multiplied by B, and you do Fy, the 2Fy front multiplied by A, minus the 2Fy rear multiplied by B, and you have exactly the yaw moment you want. So you have maximum grip and the yaw moment you want. Fantastic. You did a very good job. Now, let me ask you, what's the control there? I'm going to speak in American language. You are in deep shit. You are in real trouble. Think about that. If you turn the steering wheel more, you increase the slip angle, therefore you decrease the grip on the front. So you turn the steering wheel and the car said, no way, I'm not going to turn more. You turn the steering wheel less, you have less slip angle, and you have less control. So this is very interesting because that is the car which is winning all the race in the championship on the lap time simulation software. Yeah. And on the lap time simulation software, you don't have a driver. And then you give that to a driver, and the driver will tell you, no way I'm going to drive that car. Absolutely no way. And I'm showing this because some drivers showed me their finger time to time. So you see, the notion of control and stability must be associated with a driver feedback. And a good control for a very good driver is not a good control for an amateur driver. So you're going to have to mix the objective and the subjective, the engineer and the driver comments. So it starts to be useful. Let me show you what you can do. I couldn't explain. I mean, normally this thing needs 3 or 4 hours to explain, but I want to show you a picture of what you can do with this. This is the yaw moment versus lateral acceleration by changing the wheelbase 50 millimeter. Okay, so this is minus 50 millimeter. This is plus 50 millimeter. This is, I'm going to show you four graphs: grip, balance, control, and stability. So here's an example of the grip. I choose here spring, anti-roll bar. I need my glasses. Front toe, 1 degree of front toe is a lot. Camber, front spring, weight distribution, camber, rear toe, and so on. And I'm telling you that if you want to destroy the grip, nobody wants to do that, but the last thing you want to play with is to increase the front spring 10% because you would lose 9%. When you create this graph, you can put that in variation, or you can put it in absolute value. But on that car, may I insist, what is true for that car is not necessarily true for another one. On that car, 1 degree of rear toe is going to give you the biggest increase, about 6%. 6% is a lot. In racing is huge. People are fighting for 0.01%, okay? That is the amount of G that you can get in a corner. Now, in terms of understeer, oversteer, in variation, if you want more yaw moment, the first thing you're going to play is the front camber. And the front camber, if you want more yaw moment, you're going to have 50% more yaw moment. That's huge. But the camber is more important than the toe, than the front toe. If you want less yaw moment, you're going to have to change the weight distribution by making it 0.5% more towards the front, for example. So you can test, you start to see what you do here. You are making parametric sensitivity. Before you do your lap time simulation software, you start to, and that's not only useful when you design the car, but also when you tune it, okay? When you have design and setup parameter, like, okay, when you design a car, I'm speaking about the GT, for example, do you put the engine on the front, the engine on the rear, Porsche, or the engine in the central, BMW engine on the front, Ferrari engine in the middle, Porsche engine. So these are things you cannot change when you go on the racetrack. It's too late. Your weight distribution, maybe you can play a little bit with the ballast, but okay. Pickup point, most of the time, it's too late to change it. But setup means you can change the spring, the anterior bar, the ride height, the caster, the camber, the tire pressure, the toe, But whatever you do, you can do calculate the effect that parameter that you change on the car can have on the grip, the balance, and the next one is the control and the stability. So if you want to increase the control, it seems that 1 degree of front toe is going to make a biggest difference compared to 0.5% of weight distribution. And if you want to increase the stability, you see that in that car, may I insist, that car, if it was another story, it would be, another car, it would be a different story. But on that car, if you want to increase the stability, you need to play first with the camber. And the last thing you want to play is to put 0.5 degree of rear wing, for example. So that's the kind of things you can do. Let me show you another one here. This is the change. I'm going to show you 4 graphs. Again, grip, balance, control, and stability. And you have here 4 possibilities of tire pressure. This is in bar, 1.616 front and rear, 1.6 on the front, 1.9 on the rear, 1.9 on the rear, on the front, and 1.6 on the rear, or 1.9 all over. And here you have characters that were weight distribution, rear spring, rear anterior bar, front toe, aerodynamic balance, front anterior bar. Maybe something is wrong here because I have the front toe twice, so there must be a rear toe, rear camber, front camber, and so on. And you are going to say, so if you want to change the grip, now let's be careful here, the maximum 0.12, so that's 100 of a G, that's not a lot, okay? But if you want to increase the grip, you want to play with the rear camber, and it seems that 1.6 on the front and 1.9 on the rear will have a bigger advantage than, for example, 1.9 on the front and 1.6 on the rear. Now, balance, it's very, very different depending the pressure that you are using, okay? And balance means this is more towards understeer, this is more towards oversteer. So tell me what the balance of the car is, and I will tell you what to change. And then control and stability are here with weight distribution, rear spring, and all things like that. And the numbers are like, and then there are things in terms of control that the anterior bar on that car, again, doesn't make any difference, okay? So you know what to change depending on what the driver is complaining about. And same for stability. Rear toe, classical thing, the rear toe is very sensitive for the stability. Now, I'm going to finish this chapter by speaking to you about how you can mix that with listening to your driver, okay? So let's speak about the engineer perspective here, okay? So that car is able to take 3.36 G of grip, okay? Normally it can go in some corner as much as 5G, but you have a scaling there. The limit balance is 2,800 Newton. So it's an oversteering tendency, okay? Now, we are going to look at control on entry, and I'm going to go from 0 to 10 degree with the beta equal 0, and I have 5275 Newton meter, so 527 per degree, okay? At the apex, I only have 400, and it's normal that you have much less because at the apex, you go to the peak slip angle okay? And so you have not a lot of variation. But here, I'm already at 5 degrees, and I go from 80 to 90 degrees, and I see how much my yaw moment change, and it changed 400. That is the control, okay? Now, if you look at the stability, okay, what we're going to do is that we are going to have delta 0, and the beta will go from 0 to 1, and you have minus 463. And we're going to look at the stability when you are already at delta 80 degree, and you go from 5 to 6 degree, and you have 150. So you are still negative, but not a lot. And that means that the car will be, at the apex, is not going to be very stable, okay? So I gave you 6 magic number here from the engineer perspective, which is the grip and the balance, the control at the entry and at the apex, at the limit, and the stability at the apex also, and at the entry at the apex. Now, let's speak with the driver. And I'm going to give the driver a sheet, and I'm going to tell him, subjective, 0, the car is a disaster, 10, the car is perfect. There is no good racing driver who is going to give you a 10. A good driver is giving you at best a 9. A good driver should not be always, should never be happy, but it's giving you a 7. In terms of balance, I'm going to characterize it. 0 is neutral, minus 10 is big understeer, and plus 10 is oversteer, and it's giving you 4. And then control on entry and apex is giving you a 4 and a 6, and stability is giving you a 7 and a 7. Okay, so wait a moment here. You could see that you have 6 grade, all of them except 1. So 5 of them is from 0 to 10, and 1 is between minus 10 and plus 10. Okay, with amateur driver, we go from minus 3 to plus 3. With semi-amateur driver, we go from minus 5 to plus 5. And with professional racing driver, we go from minus 10 to plus 10. And it's unbelievable because the guys are so good, and he tell you, the balance is, I have a little bit oversteer. So it's positive number. It's not a 2, but it's not a 3 either. I'm going to give you a 2.5. Here's the thing. You are going to start to associate this number, intuitive, subjective, from the driver, with this number here, which are grip, balance, control, and stability. So you are creating a dialogue between the driver and the engineer. And for example, here, let me give an example. The guy is telling you he has an oversteer of 4, okay? And when he was happy, the number of the balance was, because it could be, the driver could be different. Let's say that when the driver was happy, instead of 2,800, he was giving you 1,500. So you know that 2,800 correspond to 4, and 0 neutral correspond to 1,500. So you know what to change, in which direction, and by how much, depending how well you are able to listen to the driver, okay? No, all the drivers are not the same. Let's try another driver here. I'm going to take this driver here, and you have grip 8. The previous one was giving you 7. So 8, 5. So the previous driver was giving you 4. So this driver, it's the same car, but the driver will tell you, I think I have more oversteer. Okay. No, here the guy in terms of control is only giving you a 3 and at the entry and a 6 at the apex, and in terms of stability, a 2 and a 3. So in other words, let's look at the number here. 8, 5, 7, 4. So this guy think there is more grip, and this guy thinks there is more oversteer. Okay, the second guy. Now the number 4, 6, 3, 6, and stability 7, 7, 2, 3. So that means that that driver is less happy with the stability of the car. And that's why you will end up having a different setup for different cars, okay? Even if they are even if it's the same design car, they will have different ride die, different camber, different pressure, because they feel the car differently. Basically, this is a tool which is not only helping you as a race car engineer or race car tuner, but also as a driver, and it's allow the people to communicate together. And that's it for the second video that I wanted to share with you, the second presentation. Now, this notion of control and stability are very, very important. This concept of grip and balance. You need to know ahead of that. Okay, when you go on a racing circuit, you never know what you're going to get. You never know, because you don't know. The track temperature could change 5 degrees and it can go from understeer to oversteer. The wind in the direction, I mean, so many parameters. But then what you do is that you have a toolbox ready with already several solutions ahead of time. In other words, you know ahead of time what to change on the car if the driver complains about understeer or oversteer. That what is the exploitation of the yaw moment versus lateral acceleration. And believe me, there is a reason why Mr. Doug Millikan spent 6 chapters out of 22 speaking about that. Grip versus balance versus grip. I really, really insist that you can play with that. You could learn a lot from it. Voila. If you have questions, I am very happy to listen to you and try to understand and try to answer them the best I can. And thank you for your attention, guys. I appreciate that.
Thank you, Claude. Вопросы? Давай. Hello.
Hi.
I'm from Bauman Moscow Technical University, and I have a question. I saw when you're tuning the steering of car, you didn't tuning your lock of differential. Why? It's also the tool.
I didn't understand. When you tune the steering, yes, what?
The tune the steering of the car. No,
the sting.
The question is, I can help. The question is when you show the examples of different tuning option to change the balance, why there was nothing about differential, limited slip differential or spool or any other options here?
Oh, you can do that with differential. There are so many possibilities. I need to find on my laptop, but yes, you can do differential. You can do weight distribution. I didn't show differential on the car, but yes, you could do it. I mean, there is so many parameters. Look, can I make a little, not trying to make an excuse here, but can I take a detour to answer your question? Okay, I'm going to show you something that is interesting here. Okay, this is a setup sheet Okay, I'm going to reduce that. This is a setup sheet that people are using. Okay, so you have torque, caster, camber, tire pressure, all the ride height, spring anterior bar, the different possibilities of setup for the damper, the gear ratio, the final drive, the front wing angle, guess what, the differential here, the amount of fuel, the rear gurney flap, and so on. Okay, so you agree with me that if I give you three spring on the front, I don't even put a number, a soft, a medium, and a rear spring, soft, medium, and stiff on the rear, you have 9 possibilities of setup, correct? All right. Now, I'm going to give you 3 ride height on the front. So you can put the car low, medium, and high, and on the rear, low, mid. So do you agree that you have 9 possibilities of ride height? Caster, I'm giving you, I don't know, 6, 8, and 10 degree on the front. And I change also the caster on the rear. So you have 9 possibilities of caster, correct? So 9 by 9, you already have 81. And I'm going to choose 24 possibilities. And you agree with me that you have much more than 24 parameters that you can change there. And so if I take 3 possibilities on the front and 3 possibilities on the rear for 24 things, like spring, bump, rubber, toe, and so on, I'm going to have 3 power 2, because there's a front, multiplied by 24, equal 3 multiplied by 48, equal 79 trillions of possibilities of setup. Welcome to intellectual masturbation. What I'm trying to explain here is that, yes, you are right, I didn't show the differential here, but there are many things that I didn't put. You speak about the differential. You know, another one that I could have put in the list here is the brake balance. It's like a big difference. So there are so many parameters that, unfortunately, I only showed a few of them. But yes, I agree with you, the differential could be there. And in the differential, you have 3 things you can change. You can change the preload, you can change the ramp angle, and you can change the number of shims, the number of active plate that you can have different. So it's a long answer to kind of excuse or justify the reason why the diff is not there. But absolutely you should do. By the way, in that case, it's a good question, by the way, because in that case, the yaw moment versus lateral acceleration is becoming a 3D diagram. In other words, you have yaw moment versus lateral acceleration with a z-axis, which is longitudinal acceleration, braking or acceleration or braking. But yes, you should be able to put the diff if you want to. We have a software called Optimum Dynamic, which is doing that for you. Yeah, definitely. Sorry for okay. Did I answer your question?
Yes, that's the answer. Thank you.
You can ask me question on this subject or general question about Formula Student or racing. It can be on tire and yaw moment, or it can be on anything else you want.
Okay, Claude, looks like everybody's pretty tired. So
yeah, it's late for you. Yeah.
Because it's late evening and the building will be closed soon here. So okay. I think we should ending our conversation so soon. And first of all, I want to say a big thank you to you. It was a great presentation. Thank you.
You're more than welcome. You know, we spent a little bit more than 2.5 hours on this. You have to understand that it's complicated. In 2 hours, I just show you what you don't know. And I'm trying to help you to be both ambitious and humble. In other words, you want to know more, but you need to be realizing that there is always something to learn, to improve. But I thank you for your attention. I am very happy to communicate with people in Russia. Let me tell you this, I have a dream. In Formula Student Germany, many years ago, I judged a team from Israel. And a few years later, I judged a team from Iran. My dream is to have them together, side by side. And I think that if people from United States and England and Argentina and so on can be together more often, I keep saying travel more and there will be less war, because you don't have to accept the idea of other people, but you have to accept that other people have different ideas. And that's one of the good things with Formula Student. We meet, and I appreciate that. And so thank you for being part of that. And I want to give a big thank you for Andre for organizing this. I appreciate your effort. Yes, exactly. And I think it's very useful for the student. And Andrea, I admire you, the time and the devotion you have for the Formula Student community in Russia in particular, and in general in the world. Thank you so much.
Hello.
Hi.
Representing all the students here, I would like to thank you for that important and interesting knowledge you gave us, and for the opportunity to use it while creating our next cars in the future. Thank you.
You're more than welcome. I'm very, very happy to being part of this. Thank you. Have a good night, and a little bit of vodka maybe. And then I wish you a good continuation tomorrow with other Formula Student judges who are also very, 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 very good.
Thank you, Claude.
Thank you. Bye-bye.
Yeah, bye.